Hey, all my polar bears and polar cubs. Welcome to Chapter 5. We're going to talk about some periodic trends. So, let's talk. The first one that we're going to talk about is the atomic radii. Now, we got a good definition, 1/2 the distance between the nuclei and the identical nuclei of the same atom if they're bonded together. But really, what we're focused on is the trend. So, as you go down a group, it increases, which let's think about. As I go down a column, I gain an extra energy level. If I gain an extra energy level or shell, I'm going to get bigger. Makes sense. As I go across, it says that it decreases. Well, the reason that it decreases is it becomes more and more stable the more electrons are in that shell. The more stable, the closer it can pull it in. So if we were going to do a high to low arrow, your high arrow would be in the highest atomic radii is in the bottom left, and the lowest is in the upper right. So if you're comparing these, which one has the largest? Well, calcium, beryllium, barium, and strontium are all in the same group. So it's the one that's furthest down, which would be barium. Sorry about that. And number 2, it says, which of these has the smallest? Well, all of these would be in the same row. So if they're in the same row, it's whichever one is the furthest to the right. So of those, it looks like silicone would be the smallest, which would be S. That's atomic radii. The next one that we'll talk about is ionization energy. Well, what is ionization energy? It is the energy that it takes in order to get an electron away from a neutral atom. So how do I make it into an ion? How likely is it to become an ion? The trend for this one is it decreases. Remember, this is what we're most interested in. It decreases as we go down and increases as I go across. Well, that sounds like it's the opposite of atomic radii. The highest would be up in the upper right, and the lowest would be in the lower left. Therefore, our high to low arrow is pointing down. Again, some questions. Who has the lowest, K or AS? Well, it's whichever one is furthest to the left, since they're both in the same row, which would be K. The next question asks which one is easiest to remove. So it's asking you which one has the highest amount. Well, they're both, again, in the same column this time. And we're looking for whichever one would be highest. So Li is above Rb, so it would be lithium. It's Li. So that would be ionization energy. The next one that we have is ionic radii. Well, it's telling us what's the, radius when it becomes an ion. So the big part that we want you to understand is that cations become smaller, and the reason that they become smaller is they lose an electron. Well, if you lose electrons, you have more protons than electrons, which means that you can pull those other electrons closer to the nuclei, which makes it, or nucleus, which makes it smaller. An anion gains one or more electrons, so therefore, if you have more electrons than protons, you can't really keep them as close. So it balloons up, as you can see here. This trend is very similar. Actually, it's the exact same as the atomic radii. And that's because it gains extra shells. It's the same reasoning, even though when we show this, our cations are mostly over here and our anions are over here. So this is the highest and this is the lowest. Okay. Are cations smaller than the original neutral atom? Yes. Lost electrons. And then the other question is, why are anions larger? They are larger. So yes. I guess we don't need the yes, but I like to say it. Because they gained electrons. Well, if you get more electrons, so if electrons are greater than protons, it's going to get bigger. And if protons are greater than electrons, it's going to get smaller. The last one is electronegativity. So what is electronegativity? Well, it's the amount that it wants to attract electrons from another atom. aka it's kind of its willingness to bond. It's the willingness that it wants to make a compound. This one decreases as we go across. Well, decreases as we go down, my apologies. And it increases as we go across. This has the same pattern as ionization energy. So it is the lowest here and the highest here, meaning a high to low is going to go this way. So who's got the bigger electronegativity, AS or N? Well, here's N, here's AS. As you can see, the numbers actually right there, it's N. What about BI and AT? You got BI, AT. Well, AT is further that way, so it is AT. Electronegativity can be found on your guys' periodic tables in the upper left. Nope, not upper left. Upper right. The upper left would be the atomic number. So let's go over some of the questions. Cesium, hafnium, and gold. Which element has the smallest atomic radii? List the trend that you used. Well, we're going to use atomic radius. Okay. And if we're looking at our periodic table, cesium, hafnium, and gold are all in the same row. So I know that atomic radius increases as I go down. So the one that's furthest down is going to be biggest. Well, they're on the same row, so that doesn't make a difference. But I know that as I go from left to right on the periodic table, they decrease. So really the question is, who is the furthest to the right? And that would be gold. For question 2, it is the list ionization energy from in decreasing order. So who has the highest ionization energy? Well, the highest ionization energy would be as far to the right and up as possible. So that would be fluorine. Then we're going to look for the one closest to fluorine. That would be oxygen. Well, I'm sorry, neon would have the highest ionization energy. Then fluorine. Then oxygen. Then carbon, and then lithium. And then with electronegativity, who has the most? These, again, are a little bit just kind of in a bunch. So we're looking at the upper right-hand corner, and of those, oxygen has the most at 3.50. So that's our trends. There are 2 trends that each have the same pattern. So let's talk about valence electrons. With valence electrons, they are the outermost shell, okay, electrons. They are also in the main energy. Well, they're in the main group elements, which if you look on your periodic table, they're the ones that have the V next to them, or not the V, the A. It goes like A1 all the way to A8 or 8A. Okay, so this would be 1A, 2A, 3A, 4A, so on and so forth. Now, they're in Roman numerals. Okay, notice the one big one is helium. Helium can only have two because there's only two electrons that can build up into it. This kind of leads us to showing valence electrons in a specific order. To me, I'm more inclined to see that you guys put them in one on each side first before putting a second one in there. When it comes to transitional metals, we always assume that they have two valence electrons. So for barium, if we were going to draw it, we would draw Ba. It is in the second column, so we're going to put one here and one there. It has two valence electrons, so 2. Si, it is in the column with carbon, so it has 4 valence electrons. If you were going to draw it as a Lewis dot structure, you'd put 1 dot on each side. Chlorine has 7. So if we came over here and we did chlorine, we'd put 1 on each side. That's 4. And then we'd put 2 on 3 of the 4 sides. Finally, magnesium also has 2. That's Mg. And we're going to put 2 dots. A little bit of a review from bio. Part of this section is going to add on to what we did in 4.3. Now, what it really is asking us is kind of what period it's in based off of the noble gas notation, what group it's going to be in. Those are the special groups that we'll get into a little bit later. And then what block, like S, P, D, and F, what type, okay, and then how many valence electrons. So, for example, on this one, we are in the third period. It is not. It is in a special group. It's called the halogens. But right now, what we would want you to do is actually not put halogens, but put V11, because that's 7 and 7A. That works right now. The block, it's in the P block. It is a non-metal. And it has 7 valence electrons. How did I get 7? 2 plus 5 is going to give us 7. So we're counting the last one. So this one is in period 4. It's in group 3. I got group 3 because if you count up the valence or the exponents on the 5, it gives you 3. This is also in the P block because the last thing is P. This would be a non-metal. Actually, it'd be a metal, I believe. It would be a metal. And then valence electrons, it would have 3. Okay, so I'm going to show you the next slide. It's kind of similar. Based off of orbital notation of sulfur, I want you to tell me how many full, how many half full, and how many empty orbitals there are. What is the sublevel with the most energy, aka what's the highest energy level that we go to, and then what type of element it is. So looking at this, go ahead and fill that out. All right. Oops. Not quite there. There we go. All right. 3, 2, and 1. So how many full ones do we have? We have 1, 2, 3, 4, 5, 6, 7. We have 7 full ones. We have 2 half full, and we have 0 empties. What's the highest sublevel? Or what's the sublevel with the most energy? That is 3p. And what type of element am I? I am a non-metal. So if you write in the noble gas notation based off of iron, so you go 1 up, that's going to be argon. And then you're going to have 4s2, 3d6. So what period is it in? Well, that's in the 4th period. That's what row it's in. What block is it in? That's the D block. And how many half-filled orbitals? Well, the half-filled orbitals would have to come from the D block. So if we just draw out 3D, it's got 6. So it must have 4 half-filled orbitals. All right, last slide. Again, let's go through this. I'm going to have you guys try it real quick, and then we'll go over it in about 5, 4, 3, 2, and 1. What period is this element in? It is in the 5th period. It is in group D. What sublevel has the highest energy? Well, that would be 4D. What type of element am I? Well, I'm in the D. That would be a transitional metal. Who am I? So if you go into the 5th energy level and you count over 5 into the D, you are TC, which is titanium. And how many total electrons do I have? Well, total electrons equals atomic number, which is equal to 43. All right, we will be doing some of those a little bit later on our next worksheet for Chapter 5. This worksheet that we're working on is just on the trends. All right, good luck, polar bears and polar cubs. Let me know if you have any questions.